Right. A little excited to be here. My name is Chen. I'm from the Technion in Stephen Frankel's study group, research group in the CFD lab. I'm going to go over quantum machine learning, mainly about waves propagation, prediction, a little teaser about the control, and let's go ahead. All right, so our research goals were, first of all, to understand if and how adding quantum layers to classical machine learning and neural networks aids in some way to solving and other things like computationally better or more efficient computations. We did it about the 2D Maxwell's equations, and also several control problems that, again, would be a little teaser here. We compared several ansatses, and we had to also add this one because we couldn't run it without making it extremely more efficient than the things are currently in the industry, and we had to cross that bottleneck in order to run anything. All right, so first of all, physics-informed neural networks. This is a classical method invented by Raisi in 2019. PDEs are sometimes very hard to solve or even approximate. For example, the Navier-Stokes, one of the holy grails of computational fluid dynamics, CFD. This is the Navier-Stokes, one of its forms, the equation. This is actually many equations because it's a differential equation. And the Navier-Stokes equation is one of the Clay's Mathematics Institute Millennium Prizes. So it's very important and widely used. Usually, to approximate it, classical methods use some sort of a grid and a discretization of some sort, but it usually can't capture the small details while being able to approximate the larger resolution, the larger features. So, as you can see, in those graphs, this is a solution to a 1D Maxwell's equation. From now on, we're going to focus mainly on Maxwell's equation. This is the solution using FDTD, finite difference time domain. And you can see the many oscillations that appear here. Even after post-processing, it's still oscillating quite a lot. Even in PADE, which is a much better and widely used a method to solve PDEs, it still has some oscillations and an overshoot. You can notice the different scales. It overshoots quite much. And this is using PINs, physics-informed neural networks, which we based our work, the quantum physics-informed neural networks. It gets a much better solution. It doesn't overshoot, it doesn't undershoot later, and it is quite smooth. So the old classical methods are not so good for every case. They're very good for some of them. All right. So this is how the architecture of the classical pins look like. You have the inputs, then in our case an RFF layer, but I don't want to get into it. It's just regular neural network. Then you get the results. There could be many outputs to that network. And there's the whole magic. Automatic differentiation is something that you can use. The derivatives are very common in neural networks, because to update all of the parameters, you need to use gradients to calculate the new ones. So if you want the derivatives themselves of the output from the input, you can actually get them for free. So yeah, you can actually get them pretty much for free, because you already calculate them to update the parameters, the network's parameters. So then you get the derivatives, and you can calculate the PDE that you want, its loss function. The PDE, if you move everything to one side of the equation, you get something equals 0. But when you go through the network, it is only approximating the actual function that you want to calculate. So you get some sort of residual. This residual is one of the loss terms. You can add more, like boundary conditions and initial conditions. But this is how you minimize the function to approximate the PDE correctly. OK? So you get the derivatives for free. You calculate the loss. And then you can approximate using the network the PDE that you want. All right, so now going quantum. Going quantum means adding at least one layer of a quantum circuit that will be instead of the classical layer. So here we have, first of all, the classical inputs, RFF layer, regular neural network, fully connected. This is the first part. The second part will be the connection to the actual quantum circuit. This will be, in our case, in angle embedding. This means Rx rotation according to its parameter, and its parameter is determined according to the results of the previous layer. This means that it incorporates the actual features that were learned by the neural network that was previously set. Afterwards, we have the ansatz. This is strongly entangling ansatz, but we tried several more. The first gate is an arbitrary rotation across the block sphere using 3 parameters, and afterwards C-naughts. Then Pauli Z measurement to each of the qubits, and its results are fed into the output classical layer, and then we get the output, and everything afterwards works as before, as the classical one. All right, these are the ansatzes that we tried. First of all, we have the basic entangling layers and the strongly entangling layers, as in Bar-Ilan. The difference here is that as many layers as you have, the gap will be bigger. Like in the second layer, you have a gap of 2 between qubits. Also, we have the cross-mesh layers, several variations of them that connects each qubit to every other qubit. All right. So going into the actual problem formulation, the Maxwell 2D equation. These are the PDEs that we solved. We normalized the permittivity and permeability to 1 just to get easier calculations and easier numbers for the precision of the CPU, GPU, whatever we used. These are the initial conditions we used. For the electric field, we used a Gaussian pulse, and the magnetic fields were 0. And the boundary conditions were especially periodic. This is the domain we calculated the first case. In the second case, we added the electric substance into the domain and wanted to see how it evolves in that. And the domain is a little bit different. The rest is the same. All right, so these are the results for a 2D Maxwell's equation using PADE. In this case, we assume that PADE is pretty much correct because it has much less of a shockwave formation than the first case I showed. So we assume it's very pretty much accurate. And those are the results for the pins and the Q pins. We used the best one was a cross mesh with 6 qubits and 3 layers. And you can see both visually that it's very close to the PADE, and also using L2 normalized error, it's very close. Also, with the dielectric substance in 0.4 in X in the domain, this is the dielectric substance. This is the PADE solution, and also the pins and the Q pins. This time it was cross mesh with 2 rotations, 7 qubits, and 4 layers. You can see that the L2 errors are very close to each other and very close to 0. So the results are quite good. And we've seen the major result is that QPin uses much less learnable parameters than the actual classical pins, like about 19% less in that case, which may not sound much, but if you take OpenAI's models that are 1.75 billion in the last models, if you take 19% of it, it's quite staggering. All right, this is in video form, the whole evolution of the system. So we had to go through a calculation optimization. We took 61 cubed points on the grid. The network was about 67,000 parameters and a quantum circuit, which is very expensive to simulate. The current packages, Qiskit and Pen-Elaine, do not perform well in such conditions when you try to go to GPU. And so we built our own quantum library. I hope it will be very soon open source and everybody can use it. It was optimized for GPU using PyTorch. And we reduced the runtime by many orders of magnitude, which made it 1.7 days to run the QPins, but it's much better than never ending in CPUs. Those are Jensen and Huang, which are 2 GPUs in our clusters in our lab. OK, so just a small teaser for the QDRL. RL is the reinforcement learning, which trains an agent to do something with its environment, to interact with it. It's kind of analogous to training a dog a new trick or losing a bad behavior, using a carrot and stick. You get a reward or a punishment. The main benchmarks are like Atari games and things like this, but many other things. The quantum soft actor critic is the newest one we tried. You can see that the hybrid one, which consists of 2 critics, both one classical, one quantum, performed best among the classical, and the quantum. And for this kind of a solution. And we also have, we tried using it for CFD. It's only preliminary results. So in conclusion, we reduced many of the parameters. In smaller problems, it was about 30 to 40%. And the future work, we hope to get it for much larger and deeper networks. This is the group. It was a group effort. Also, Noah the cat helped a lot. Thanks a lot for listening. Any questions?
Thank you very much, Steve. Any questions?
So my question, is it possible to solve directly the differential equation of the quantum computer?
I don't know of any method to solve it directly on a quantum computer. There may be things like quantum annealing and things like that may be able to do it, but I'm not aware of any work that did it currently.
Just a comment. In fact, you can do it, right? People solve the fluid dynamics on a quantum computer. You just use HHL, you linearize the equation, and then you...
Yeah, but it's, I mean, it's not currently possible. It's not like you can...
People did it. It was not very effective, but there is a...
Yeah, HHL is not quite NISC friendly, so you can...
There's a work which I can give you the reference by Rolls-Royce, actually, who solved computational fluid dynamics problem. But actually, my question is more general. Maybe your group you thought about it. The problem with nonlinear PDEs is that they are very sensitive to initial conditions, particularly, for instance, turbulence. So even if you train the system on many types of initial data, when you reach the turbulent regime, the solution deviates exponentially from the one that you're supposed to get. And it's a problem for machine learning, classical, and quantum. So
Yeah.
I don't know if you guys thought about it, whether you can actually enter the turbulent regime, or you have to stop before that, or before the chaotic regime.
Yeah, this is in like many steps before this kind of work. But yeah, entering this kind of regime would be problematic, and we still have to think about it, how to work with it. But thanks for the comment.
I think we have time for a couple more questions, but before that, Norm, Romy, could you please come in the times? Yes, there were more questions. Yes, Noga?
If I understand correctly, your architecture is built from two connected parts, so you have a classical neural network and then the quantum ansatz. Have you maybe tried, or why is it not possible to optimize the classical neural network, get the weights, and then only run or optimize the quantum ansatz? Like, why does it have to be connected?
There may be several architectures, different architectures that you can think about. You can train only the classical one and then the quantum one, but we think that incorporating the quantum layer into the whole architecture could help reduce the parameters and get much better results this way. But it may be possible, like training it like once every 10 epochs or 100 epochs to reduce the cost and still be able to incorporate it inside the network or things like that. It's an interesting idea. Thanks.
Okay, maybe last final, but please, Norm. I got you now, so please come to the stage. And I think Guy has a question. No? Oh, sorry.
Did you find any case where the quantum layers did something that the classical layers could not?
I wouldn't say could not, but as I showed in a QDRL, it got better results. Like in the quantum soft critic architecture, in the inverted double pendulum problem, it performed a bit better. Still, it's C-dependent and everything. It may be like an anomaly, but it performed better, getting faster rewards and a higher reward at the end. So I wouldn't say that it's a quantum advantage, but it's still a pretty optimistic thing to see in the results.
Okay, let's all please once again.
Thank you.